So we'll just continue. We're going to have to use long division in this example before we integrate. Like I was saying, the denominator is not a linear factor, so you have to actually do the long division. I always forget what this looks like. So my denominator goes on the outside. My numerator goes on the inside. Okay, I need to multiply something by x squared to get x squared. It's a 1. So 1 times x squared is x squared. 1 times 1 is plus 1. We subtract, and I'm left with just an x. So now I'm ready to write my polynomial over divisor equals quotient plus remainder over divisor. So this integral is equal to my quotient, which was a 1, plus the remainder, which was x, over my divisor, which was x squared plus 1. And now I'm ready to integrate. So I'm going to break this integral apart into two pieces because it's a sum and difference, and I'm allowed to break the integral apart only in sum and difference. So the first part of the integral is just an x, because the integral of 1 is just x, plus. Now the second part of this integral just becomes integration by substitution. So I'm going to let u equal x squared plus 1. My derivative is 2x. I'm automatically going to multiply the dx to the other side. You'll notice I'm missing the 2. I'm going to introduce the 2 on the top and bottom. So this 2x dx is 2x dx. My u is the denominator term, and the 1/2 is floating around. So this is x plus 1/2. My integral becomes 1 over u du. And then it becomes x plus 1/2 ln absolute value of u plus c. Because I don't have values, it's an indefinite integral. X plus 1/2 ln, my u was x squared plus 1, and then I add my arbitrary constant. Now, sometimes you'll have to do some funky substitution just like we did before. So if I do u is equal to x plus 1 in this example, you'll notice that my derivative is just dx. Or my derivative is just a 1, and I can multiply the dx over. But again, now in this example, I have an extra 2 floating around, which is not a problem. I have an x that's floating around, which is a problem. So I need to take this expression and isolate for x, which would be u minus 1. So I'm going to come back. The 2 still stays with my integral. I'm going to pull it on the outside because it's just a constant. This becomes u minus 1 for the x. My du and dx are identical, so I'm just going to add a du there. And my denominator was u squared. So you can see this is a little bit of a funky integration, but it still works because I can break up the fraction. So u over u squared du minus 2 integral 1 over u squared du. This becomes 2 integral 1 over u du, which we know is the ln function, ln of absolute value of u. Minus 2. Now this one just becomes power rule, but I need to bring the u up to the numerator. So I'm going to add 1. So u to the minus 1, divide by the minus 1, plus my arbitrary constant, and I'm ready to sub my u back in. 2 ln x plus 1 plus, because these two negatives will cancel, 2 x plus 1 to the minus 1 plus my arbitrary constant. Again, you can always take the derivative of your answer to go back and check. In terms of guidelines for integration, you know your basic integration formulas, which are the reverse of antiderivatives or reverse of derivatives. You need to know those, and then you need to know u equals an appropriate u so that you can try to do integration by substitution. These are the only methods we are going to learn in this course, so you need to make it look like an easy antiderivative formula or something where you notice the derivative as part of the expression and do integration by substitution. Now, in an example like this one, I know that the derivative of ln x is 1 over x, And you can notice that there's a 1 over x sitting right over here. So this actually works out really well because it does work out to integration by substitution, even though it looks kind of weird. So my du term is 1 over x. And you're going to notice that this is like a differential equation. So dy is equal to 1 over x ln x dx. It's kind of like our separable differential equation. I isolate the dy differential from the dx differentiable. I integrate both sides with respect to x. This becomes y equals 1 over x dx becomes my du term. And then my denominator was my u term. So this is 1 over u. So my y is equal to ln of absolute value of u plus c. And then I come back and sub my u back in. So ln of ln x plus c. Now you'll notice if I want to check this, I just take the derivative. The derivative of ln of something is 1 over the something. The derivative of the something would be 1 over x, and the derivative of the constant goes to 0, and this matches up to my original derivative. With trig functions, sometimes you're allowed to do integration by substitution. There's no set out formulas you know, so you just have to kind of rework this to make it look like integration by substitution. Tan x is given by sine x over cos x. I know if I let u equal cosine x, which is my denominator term, the derivative is negative sine x, and then I multiply the dx over. You'll notice I'm missing the negative sign, so I'm just going to introduce it on top and bottom as a negative 1. So my du term is negative sine x dx. My u term is cos x, and the other negative is just floating on the outside, so negative 1 over u du. And again, you're going to be noticing that the majority of this lesson turns into the ln formula, which is what we're working on. Ln of u plus c with the negative out front, so negative ln of cos x plus c would be the integral of tan. The derivative of the secant formula, this one is a little bit weird because you have to do a trick, and if you don't watch this trick, you will not be able to integrate this. So this is a trick, and you kind of see it once and then hopefully remember it. I know that the derivative of secant x is secant x tan x. So what I want to kind of do is introduce a sec x plus tan x on the bottom and top. And it again, if you hadn't seen this before, this one is a really hard problem to integrate. This is my little trick term. I'm going to multiply top and bottom by sec x plus tan x, and I don't change the question. Now you'll notice that if I let u equal my denominator, sec x plus tan x, the derivative would be equal to sec squared x, whoops, not sec squared x. The derivative of sec would be sec x tan x, plus the derivative of tan would be sec squared x. And I'll put the dx on the left and multiply it to the right, so there's my dx. So if you look at the numerator and I distribute this out, I get sec squared x plus sec x tan x, which is actually my derivative term. So this orange part ends up being my exact numerator, so I'm going to call this du. And then the sec x plus tan x ended up being what I used for my substitution, which was 1 over u. My integral becomes ln of absolute value of u plus c, and then ln of sec x plus tan x plus my arbitrary constant. So if you don't remember this trick term, you are probably not going to remember how to integrate secant, and it does come up in the future quite a bit, so try to recall that information as you need it. Now they give us here in this table the integral of the 6 main formulas. You won't be given these on a test, so it's better to kind of just know how to do them when you need to. So not given. Depending on if you go to engineering or not, sometimes they will give you a data sheet, but if you're in the regular Math 265 or an equivalent of that, you won't be given this as a formula sheet. Now in this example, I wrote down an identity here, which I always forget. 1 plus tan squared x is sec squared x. So you'll notice that this question requires me to simplify this function a bit. The integral of 1 plus tan squared x dx, I'm going to replace that using the identity. The square root of sec squared x becomes absolute value of sec x. Now, from 0 to pi over 4, secant is always positive anyways, because secant is related to cosine, and cosine is positive in quadrant 1. And 0 to pi over 4 is in quadrant 1. So I'm going to drop the absolute value, because it's the same thing. And in this case, we just integrated secant in the question before. So in this example, I will use the table. This would be ln of sec x plus tan x. And then I'm just going to evaluate from 0 to pi over 4. So this becomes ln of secant of pi over 4 plus tan of pi over 4 minus ln of secant of 0 plus tan 0. And then secant of pi over 4, cosine of pi over 4 is root 2 over 2. So secant would be 2 over root 2. Tan of pi over 4 is 1. Minus secant of 0 is 1, and tan of 0 is 0. And the nice thing is ln of 0 or ln of 1 is 0. So this just finally works out to ln of 2 over root 2 plus 1, and there we have it.